Okay, so Newton's law of gravitation with frequency and period. How many of these problems have you worked on in class?
None of them.
That's a good start. Yeah. What force of gravitational attraction exists between two 0.10 apple? Okay, well, let's just start off by just writing out the actual relationship here. So the law is F equals G times M1 M2 divided by R squared, right? So basically this is explaining the gravitational force of attraction between two masses. So let's say you have mass number 1, we'll call it A, and mass number 2, we'll just call it B. So R here, this R term, represents the center to center distance between the two masses. Alright, so it's literally the center to center distance, because the thing is, usually what you sometimes they ask you the force of gravitation between two planets, right? And if you're going to apply this law, you need to know the radii of the planets, right? And because you're gonna have to include that. Yeah, you're gonna have to include that in the R term in the bottom. So let me see here. Also G. What's the value of G?
6.67 times the negative 11 power.
Okay. Times 10 power minus 11. Units is newtons times meters squared per kilogram squared. Okay. Your first problem, what's the force of gravitational attraction between two 0.10 kilogram apples that are 2 meters apart? Right? And, well, yeah, that one is, that one's pretty straightforward. Okay, number 2, what force of attraction does the Earth exert on one of those apples? What force does the apple exert on the Earth? Okay. Why? How come they're going to be the same?
Well, because if you like hit something, then the force that you exert onto that thing is the same as that thing exerting on your hand.
Okay, so that's Newton's third law.
So if something falls to the ground will also, we're getting a club to that thing.
Right. So I see what you're saying. Force of an object on another object is equal to negative the force of that other object on the first object. Right? They're exerting the same equal forces. Right. So if you get the force of interaction, the force of attraction between the Earth and the apple, it doesn't matter which way you go, apple to Earth, Earth to apple, it's the same force. Right? And the way you know that is because of the equation over here. So really, if let's say M1 was the Earth and M2 was the apple, right? Then you can apply this equation to both. It will give you the same result. It will give you the same result.
So it's just the same. It's just the same thing. Just pick one and put a negative.
No, it's not that you pick one of them. I mean, yeah, suppose we're saying force of the apple on the earth, right? So we can apply this gravitational law, and let's say m1 is the apple, m2 is the earth, right? We can calculate it, get some number, right? But then if we switch it around and say, okay, m1 is the earth, m2 is the apple, right? We still get the same magnitude of force. Of course, they're going to be in opposite directions. That's all that the negative sign means, opposite directions. But in terms of the actual number, it's the same thing. Okay. Let me just give me a second. I think I have a couple of gravitational force problems that we can work on. All right. Wow, it's pretty big. I think I can shrink it a little bit. I'll just put it over here. Is it good?
Yeah.
Okay. Let me see. Erase a few things here. What's geosynchronous mean? Right, so that means it rotates with the same period, or it orbits the Earth the same period as the Earth rotates, right? And since it does that, that means that it remains above the same location on the Earth. Okay, so that's the first clue to solving the problem, is that the satellite is geosynchronous, which means that its period has to be the same period as that of Earth, right?
Yeah.
And since that's the case, it could allow us to solve for different things. Maybe how high up it is. Well, it tells us the orbital radius anyway, so we're pretty good with that. But the first question is the calculated speed. Right, that's the first part. So what I'm gonna do is I'm going to I'm going to show you how to derive the equation for the speed of the satellite in its orbit. And what I want you to do is to using the same kind of analysis, try to come up with an expression that represents the period, right? The time period that it takes for the satellite to, travel once around the Earth, right? To revolve, to complete a full orbit. So, since the satellite is going around the Earth, is in circular motion, right?
Yeah.
So we can say that the centripetal force of the satellite on the satellite towards the Earth is the gravitational force, right? So we can say that G times m of the satellite, m of the Earth, divided by r squared is equal to m of the satellite times its velocity squared over r. Exactly, because in this case, the gravitational force exactly is applying the centripetal force. So that, no, we're not considering any sort of resistance or. Hmm.
Yeah, so what I'm saying is the gravitational force is the same thing as the centripetal force because there's the net. The gravitational force is the net force.
Exactly. Yep.
There's no other. There's just
Nothing else. No friction.
yeah.
Nothing else. So
Don't you need to know the satellite?
no, that's the thing. You don't, right? Because they cancel out from the equation.
Right.
Exactly.
Except for velocity.
Hmm.
Okay, so that's yeah, 6.67.
Well, let's not plug in the numbers just yet because we want to see how the velocity is related to the radius. Right? That's what we're trying. We're not trying to. Let's not plug in the numbers just yet because there's something better that we can get from this. So let's go ahead and we'll just cancel out the radius from one side and one of the radius on the left side. Right? And we can say that now we have GME over R, right?
Equals velocity squared.
Exactly. So let's solve for the velocity. All right, that's our relationship for the velocity.
So now we should solve.
Okay. So go ahead and put in into your calculator. Solve for the velocities. Tell me what you get.
Okay, so get square root.
I think the mass of the Earth is. I think mass of the Earth is 5 point. I think 5.98.
It's 5.1.
Yeah, you.
Definitely got it.
Yes.
The mass of Earth. 6 times 10 to the 24th.
Okay, so it's 6 times 10 power 24.
Okay, cool. Times the mass of the Earth, or sorry, 6.67. 67 times 10 to the 24th. Yeah, divided by which is
What about the radius of the Earth?
10. The radius of the Earth.
Mm-hmm. What's the number for that one?
Um, 6 times 10 to the 6.
Mm-hmm. Okay.
Do you need that?
Yeah, we're going to. Oh no, actually, you're right. We don't need the radius of the Earth. We just need the radius they gave us, right? The radius of the orbit.
Yeah, so
True. So.
4.256.
Mm-hmm.
4.256.
Okay, let me see what I get. Ten power 7. You said 3075, right? So you got V equals 3075.87. 3075.87 meters per second. So that's the speed that the satellite has to be traveling with in order to maintain that geosynchronous orbit.
Yeah.
Okay? So you see the same way, the way we got a function or an expression for the velocity, I want you to basically analyze the path of that satellite and calculate the period of that satellite. Okay, the period is the time it takes for it to complete one full revolution around that circular path. Okay? So since you have an expression for the speed, and also you can get an expression for the length of the path around that circle, right? You can use those two to get the period. Mm-hmm.
So it would just be diameter 4.23.
Well, don't solve it just yet. Get an expression for the period, and then we'll use that to solve for it. You got 40. Let me see something. You said 43,000. 43,000 what? 0.929, right? 43,181.929. I feel like you're missing a factor of 2 here. Let me see. Let me just...
So I rounded it to 3.14.
Oh, did you just do pi times r?
Pi times, oh, whoops.
2 pi r, right?
Forgot to
Okay. Because...
okay,
okay, that's correct. Because what I did was I divided what you had by 3,600, and I got 11.99, right? Which is pretty much 12 hours, half a day. You're supposed to get 24 hours, a full day, right? So you were off by a factor of 2, because it takes the Earth to rotate. It takes a full day for the Earth to rotate one revolution, right? So it's going to also take the satellite a full day, 24 hours. So you have 2 pi r divided by v, and v is this expression over here. So this is 2 pi r multiplied by the square root of r divided by the square root of g times mass of the Earth, right? So on the top, we're going to have r to the power of 3/2. Because if you multiply r times square root of r, you get r power 3/2. Okay, and this is your period. Okay, so the period is proportional to 3/2 power of r. Okay, so with this you can really compare the period of revolution between different objects in orbit. Okay, and keep in mind that these formulas, they only apply to objects in orbit, in orbital motion, circular motion, but they're in orbit, right? Not rotating objects. Okay, so yeah, that was pretty good. Yeah, that was pretty good. Let me see. So, right. So this is where you guys left off, right? The Newton's laws. Okay. So we'll leave it here. We'll cut it off over here. Next week, whatever you gather from class, whatever new topics that you get, just give me a heads up, maybe a couple days ahead of what you guys are covering, and I'll prepare a few maybe practice sheets that we can work on, depending on how many, of course, how many practices or homeworks you have.
Yeah.
Yeah.
That sounds awesome.
All right, man. Any questions?
I think I'm good for now.
Okay, good, good.
Thanks so much.
You're welcome. Have a good night.